All right, welcome back, everyone. Hope you guys had a good weekend. So I know it's kind of warm in here. Unfortunately, there's nothing I can do, so I left the door open. Hopefully, cool air will somehow cycle in, but I doubt that will help much. Okay, so if you feel a little warm, feel free to step outside and get some cool air. Okay. I can't actually affect the temperature in here, so it might get a little warm. I felt that yesterday when I was lecturing in here. Okay, so hopefully we can get cool air. It's currently 77 in this room. That's kind of too warm for my liking, but okay, we'll somehow deal with it. Any general questions for me? No. So the first quiz Thursday, very straightforward. You know, be able to draw Lewis structures, simple organic structures like CH4, C2H6. So if you could do that pretty comfortably, like the stuff we drew last week, you'll be fine. Calculating, determining formal charge. So if I give you a structure of an atom or of a compound, and I point to an atom. Without its correct formal charge, be able to predict what it should be based on if it's nitrogen, oxygen, sulfur. Well, let's just say oxygen, nitrogen, a halide, and I think that's it. Oxygen, nitrogen, carbon. Sorry, I almost forgot the most important one. Carbon. Okay, and then the last thing I probably you should know is, the active has some questions about sigma bonds, pi bonds, be able to identify, how many carbon-carbon sigma bonds are in here, carbon-carbon double bonds, or pi bonds, etc. So no drawing skeletal structures just yet. I feel like we just touched upon that. So, and we're going to get more practice drawing skeletal structures in Thursday in lab, okay? All right, and then the active homework is due on Thursday. By Thursday, we would have covered hybridization and resonance, and that'll be chapter 1. I haven't posted chapter 2 because we haven't even gone to acids and bases yet, so I won't post that until probably on Thursday. Okay? All right. So, as usual, please sign in here. Today is the 19th. Well, guys, we haven't gone over that much, so yeah, that's it. All right, so last time we were talking about condensed structures, and I just want to go over a few more examples because there's a lot of different ways, you might see this. All right, so what we should do, let's do this first. Start with this, write condensed formulas for these structures. Okay, so write condensed formulas for these structures. So here's one. So something like this is similar on the homework. How do we write condensed structures, formulas, for things like this? Okay, so you have a ring here. Might be a little bit tricky. How do we write a ring as a condensed structure? So the only real way to write this is if you condense this portion here into its atoms, okay? So we count all the carbon atoms around that ring. All right, that's called a benzene ring or a phenyl group or an aromatic ring, okay? So this has 6 carbons And if we count the hydrogens, there's 1, 2, 3, 4, and 5. So this is abbreviated C6H5. Okay, C6H5. So that's the common abbreviation for this type of ring. So whenever we see this abbreviation, that means this ring structure is in the compound. Okay, and this ring is everywhere. It's like in agrochemicals, in pharmaceuticals, everywhere you can imagine. It's even in your food as a preservative, as a benzoate. All right, like sodas and processed stuff. All right, so that's the ring, and a common way to abbreviate this, the rest of the molecule here is you're going to have a carbon. Okay, so a carbon, and then there's two ways you can abbreviate these two oxygens here. So let's write from left to right, C6H5. And then we go right here, we're going to have C. So there's two ways you can write this. C, you can write O, and then another O, and then what comes at the end? CH3. So you can abbreviate this, or you could write C6H5, CO2 if you want to abbreviate it, CH3. So you might see this in either these two ways on the homework and in textbooks and in this class, okay? All right. So if that ring didn't have double bonds, well, you'll just have a different number of hydrogen atoms there. So it'll be pretty much almost the same kind of procedure, okay? So that's one way you can see the ring abbreviated. Now let's talk about a few other examples here. What if you have something called symmetrical ends? So what if one end is symmetrical, okay, or symmetrical branches? What if you have a situation like this where let's undo that. Sorry. My bad. Okay. So let's write the condensed formula for this. Okay. So what's special about this one, at the very beginning to the left, you have 3 identical branches. All right. So the proper way to write this is if you have multiple ends that are the same. So like on this one carbon atom, right? See that carbon atom where it has these kind of twigs branching out? The best way to do this is you put the identical ends in parentheses. So here we would write CH3, CH2. And how many of these do we have? How many of these groups can you see? 3, right? Because that's the beginning here. CH3 here and CH2 there. So you're going to put 3 there. And this carbon here, that's this carbon right here. Okay? So that carbon I just drew without parentheses, that's that starting point right there. That's the proper way to write this, this condensed formula. And that's because if you were trying to see which branch to start out with, if they're all symmetrical, you can't really pick one. So you should start your counting at that carbon I circled, okay? So let's just continue here. So you got CH. So that CH is right there, okay? Now up in, the only time we put parentheses if something has carbon in it. If it doesn't have carbon in it, you don't have to put parentheses around it. So, but you could if that helps you. So this one, I'll put OH here because that's the OH group there. All right, and then the rest of here we have CH2, 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 okay? And then the last part, we gotta be careful. We need to abbreviate, that's called an aldehyde, okay? Very sensitive compounds. You can't write COH, And the reason is, if you write COH, you're implying that that's an alcohol, an OH group, but it's not. So we have to write the C first, H, then O. So when we write it this way, this implies that the H is actually bonded to the carbon and not the oxygen. Okay, so you want this way when you're writing this compound. So aldehydes is always this way. So this here is an aldehyde. This is an alcohol. All right, are any questions on that example? So you have to do a lot of practice with this. That's what Thursday is for, to get the hang of these type of structures. Okay? All right. Yes?
I have a question.
Yeah.
Can you explain the parentheses part again? So like.
Yeah, sure. Right. So parentheses are used for when you have things branching off the main chain, or when you want one side, or say one end has multiple of the same group on it. To represent that accurately, you should put those all in parentheses. Okay? So if I just had two of these here, I would just put a 2 outside of here. Okay? That's the more proper way to write these condensed structures. You can write it a little bit differently, like the homework has you do it. So if you just wrote it like this, CH3, CH2, and then you did this, C, CH2, CH3, 2, and then you continued on to the rest of the structure, that's technically correct too, but it's more proper if you do the first way. So this is the better way. This is okay, but not technically correct. Correct. Technically, okay. Technically speaking, it's not correct. You could write it better. Okay, so the more condensed it is, the better the structure is, the more easy is it to interpret. Because if you see these three, if you see, you see these three groups here, right? You would say, okay, those groups are just attached to the same carbon, so I should just write it this way instead of reading it this way where, okay, I have a CH3, CH2 group, and then to that same carbon atom, I have 2 other of those same groups. Isn't it better we just condense right away, right? So that's the reason why. So I'm going over all these examples because these are like all the times you can see where parentheses are used. And it's not so straightforward as just when something branches. There's also other places where they're used too. Just so you're aware, okay? But any other questions about, I'm going to do one more example for repeating, using parentheses. And then I'm going to go over the do's and do nots when you're drawing these structures. Okay? Yes, Captain.
Since we have like multiple CH2s in a row, is
Yeah.
there a way to shorthand it in any way?
Oh, you mean from like in the way I wrote in number 1?
Yeah.
No, I wish, yeah. But there is a way to abbreviate this, okay? And I'm going to go over that right now. All right, so that's symmetrical ends. So I'm just going to put a little box over here. All right, so repeating units. All right. So this is one we have. So use parentheses when there are 3 or more of the same unit repeating. So let me just clarify that this does not mean that they are attached to the same atom. This means when they're repeating in a row as you go down a structure. Okay, I'll give you a few examples here. Okay. All right, so if we look at this structure right here, oops. All right, so you see here on the left side, okay, how many CH2 groups do we have on the left side? Well, we need to remind ourselves, remember, these groups are CH2s, and these groups are CH3s. All right, so how many CH2 groups do we have in a row? Three. All right, so instead of writing CH2, 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 we could abbreviate that. Because imagine you have, I don't know, let's see, linoleic acid. That has like 16 CH2s in a row. I don't know if you want to zigzag it all and write all 16 of them. You might miss one or two. So you can just abbreviate it. So let's start from the left side, CH3, and then in parentheses, CH2, 3, CH, NH, oh, sorry, that's an N. What am I doing? CH, NH2. All right. And then if we continue here, CH2 is right there. And then for this one, you could just write it in order here, CONH2. Like that. Okay? So something like that. That's when you can abbreviate. You can also abbreviate it when you have similar type of, like this. Let me draw another one. So what if you have something like this? Okay. All right, I just made that structure up, but all right. So let's look at what we have here. We have a CH3. And notice here that we have several alkene atoms here. 1, 2, 3, 4, 5, 6, 7, 8. So what you can write here is, oops, let me just clear up my drawing here. So how many CH did I count at first? Was it 6 or was it 8? I think it was 8, right? So remember, each CH represents an alkene because right here, we technically have H's still here, okay? Right here. So if we count how many of these H's we have, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 of them. So we could write here 8 and then CH2, Br. Okay? So we can only repeat when they're the same functional group. All right? So you can't write, you can't repeat, you can't do something like this. C4. Say you have 4 carbon atoms, right? Say one is bonded to 4 other carbon atoms and one's an alkyne. You can't do that. You can't abbreviate that. They have to be the same functional group. So see, or the same pattern. So see here, in this example, the second one I drew with the bromine, all of those CHs came from the same kind of double bonds, right? So that's why we can abbreviate it. And the first example with the nitrogens in it, all those CH2s were CH2 groups bonded to 2 other carbon atoms. So that's okay too. So that's why we could abbreviate it. All right. So when I introduce abbreviations like this, students will try to abbreviate everything. Don't do that. Okay? So that's why I gave you these 2 examples to point that out. Are there any questions on repeating? Catherine.
So the first one, so we can have the NH2 that's breaking up from the CH in parentheses or not.
Oh, is it?
It's like CHNH2.
Is this one?
The other one. The NH2 that's breaking, going up.
Oh, okay. Oh, NH2, that one. Yeah, so you don't have to put in parentheses if you don't want to. Yeah. The only ones that have parentheses, they must have carbon atoms. So if that had a carbon atom attached to it, you would have to put in parentheses. So say it was NHCH3, you would have to indicate that that's a branch and that's in parentheses. Yes.
So that's a case where you can put parentheses, but you don't have to put
Yeah, so as long as it doesn't have carbon atoms sticking out of the branching part, you don't have to put parentheses. But you could if you want that for, simplicity, yes.
Okay.
Yeah. All right, any other questions about repeating units? Okay. So now let's talk about drawing these structures. So you may have noticed I drew these structures in specific ways, and that has to do with how they actually look like in real life. Okay, well, under if we were able to see the structures, based on crystal structures, you can. All right, so now let's do here, drawing correct structures, I guess. All right, so the point of this is to represent all shapes accurately. All right, so say I have this structure right here. Oh no, that's probably the bad color. So this is a correct form of this structure. You do not want to do this. So don't do something like this. Oopsies. What happened here? I did not mean to move stuff. Oops. All right. So something like that. All right. So notice the only difference here is I drew the okay. So when I refer to branches, they're commonly called substituents or attachments, but we usually call them substituents. So you'll hear that word a few times. Okay. It's like substitute, and it sounds like constituents. But substituent is like something substituted off a main chain. All right, so the only difference here is I drew these groups, right? I drew these groups the opposite way. So when you build these structures using models and stuff, you'll see that the structure on the left, that's how it really looks like. And the structure on the right, that's it being incorrectly drawn. Because you might think, oh, does it matter how I draw these structures? Or can I be like arbitrary with it? Can I just draw it however way? The short answer, no. Does it matter in terms of how it looks like here? Not really, but if you go draw these things on, if you go visualize these things in like simulations on molecular models, they do matter. So it will affect your perception of how these molecules actually look like. And remember, as opposed to general chemistry, we think about the actual structures in organic a lot more than previously you did, okay? So you never want to draw like that. Now, would I take points off if it was drawn like that? Maybe for like the first few quizzes, I'll probably let it slide. But when it comes exam time, that would be unacceptable, okay? I'm not saying I'll take like a majority of points off. I'll take like 0.5, okay? So it does matter here. Okay, are there any questions about that first example? I'm going to do another one. Okay, so when we draw it down, like on the right example, when we draw it down or, pointing away from, like the point, that's called like the cup of the structure. You point it like that, that's technically incorrect. But there's times when you have no other choice and you can do that. And I'm going to show you another example of what I mean, okay? So you want to try draw. So draw practice like that. Have a branching substituent. Have it extend from the angle, like the point where it angles off, okay? So here's another example. Okay. Boop, boop. All right, so there's two ways this can be correct. So this is a correct way to draw this structure. Notice I did not put any of the branching substituents towards the interior of the, say, angle. I put it outside where it meets at the point, okay? Now, this is also a correct way to draw the structure. So say I start like this, okay, and I draw those three lines first. This is also correct as long as there's two branching points on this carbon and that the smaller group, okay, the smaller group is the one pointing towards the inside of the angle, say, okay? That's fine. So this is the smaller group. All right. Now, where's the situation when that's not okay? I'll draw that next. So this is also correct. All right. So this is this would be considered horrendous. So don't do this. So this, something like that. Already a big no-no. Okay. And you get these two flipped. All right. So this will be considered incorrect because one, these two groups on the far left here, they look like you made like a little umbrella. No. The reason why we don't draw like this is because it doesn't depict the tetrahedral shape of the carbon atoms correctly. So you don't want to do that. Okay. And also, this area right here, the smaller group is not towards the inside of the angle. So that's technically incorrect as well. So don't draw like this. Incorrect. Okay? Another way to get the hang of this is just to do practice. Okay? Not just by looking at these structures, but actually doing some practice. Okay? Are any questions on that? Okay.
So how do you know when it's like acceptable to have them like going up or down for it to be correct or incorrect?
So it's only you look at if you have like at that carbon, if there's like two different branches coming off of it, and so it wouldn't matter if these were the same, but if one's smaller, you should have that smaller one pointing towards the interior, and that's just because if you look at these things, if you look like bird eye view from them, you'll see them like kind of drawn in this way. I'm not very concerned with like this kind of distinction. So like this distinction here. I won't really police that. Okay. What I really don't want is something like this. Okay, I'll be looking for that. But for the ones that are coming up or down, honestly, there's really, I think it's more like part preference of like how things are drawn here. But I'll just say it's more technically correct if you do it this way. Okay? And that's because the bigger group will occupy more space, so it should be coming at you or, be extending from that zigzag. All right? But I know it's kind of like very specific. But I won't. If you draw like that, it won't bother me, okay? But usually, how should we always draw? I say you should draw like this. This is the best way. You avoid that problem altogether, okay? And we'll learn why these things are drawn this way. If you build models, you'll see the perspective. During one of the lab days, we'll work with micro models on 2 occasions, and we'll see like why this is. Okay? All right. Okay, so that's drawing structures. Okay, it's kind of an art form here. Okay, any questions? We're gonna stop there for drawing structures for now, and we'll revisit this much later. We'll be drawing all throughout this course, and on Thursday we'll have a lot more practice with these. Okay? All right. So now let's talk about the shapes of molecules, how to predict the hybridization on the central atom. All right, so let's shift gears here. Shapes of molecules. All right, look at central atom. All right, sometimes you'll have more than one central atom, so we have to look at them individually, okay? So here are some common examples of each geometry we're looking at. So, acetone in nail polish remover. All right, so this molecule has 3 central atoms, all the carbon atoms, okay? So this CH3, what shape is this? Tetrahedral, planar, or linear? Thank you, yes, tetrahedral. Good, so both CH3s they're symmetrical, so that's why they're both the same geometry. Now, if we look at the center one, you notice here that there's only 3 regions of electron density around it. So it's not going to be tetrahedral. It's going to be planar. Do we all agree? Okay. So, and then if you look at this bond angle here, so if you look at this bond angle, so this bond angle is approximately 116 degrees. So that's close to the theoretical value of 120 for trigonal planar. Because remember, a triangle, each angle should be 120. Okay? Now, what about, let's go to nitrogen. All right? So let's look at nitrogen. Because nitrogen also can form 4 bonds, or have 4 electron groups around it. All right, does everyone know what these mean? These shaded and hashed lines. It's supposed to give you 3D character information about a structure when written on paper. Okay, we'll see this a lot. Not right now, but later. So this is how you represent the tetrahedron of this shape. But it's not tetrahedral. The shape is actually, what's the shape for N here, actually? It's not tetrahedral. It looks tetrahedral, right? But what is it actually? Yeah, so you can say trigonal pyramidal or just pyramidal. Okay, but that's exactly right, pyramidal. Good. All right, and you see these bond angles. This bond angle, 110. Don't worry, this is just to illustrate. And this bond angle is slightly different. Bro, stop. Oh my God, okay, whatever. It's too smart. Maybe if I just do that. Okay, yeah, here you go. So overrid the computer. The AI here. I think that's AI, I don't know. All right. So you see here, they're close to the observed tetrahedral value, or the theoretical value in methane, right? 110. Very close. And we see that difference because of the pyramidal shape. Okay? Good. So nitrogen actually doesn't adopt a full tetrahedral shape. It's going to be pyramidal. Okay, let's look at now oxygen. Carbon. All right, so we look at this bond angle here. That is about 108.5. So that's pretty close to, that's actually a little bit larger than water. Okay, and that's because of the methyl group, actually. Because of the overall shape of it, okay? But this oxygen here, what's the shape of this oxygen? Is it bent? Good. Not tetrahedral exactly, but bent, right? Bent shape. Good. Okay, so we got tetrahedral, planar, pyramidal, bent. Okay, so let's go over a few more. All right. How about these carbon atoms right here? What's the shape around each of those carbon atoms? Linear, because look at this molecule, right? It looks like a line, so that's linear. All right. So we also have, we can also have shapes around phosphorus and sulfur. So they will also have hybridization schemes that we usually give carbon and nitrogen and sometimes oxygen. Okay. So here's a phosphate. All right, so these bonds, the OPO bond, is usually around 110 degrees. So this is considered to be pretty much similar to methane, so it looks like a tetrahedral shape. All right. So we, if we were to give this a hybridization, what's the hybridization for tetrahedral? sp3, sp2, sp? sp3. So most of all of these so far are sp3, 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 and specifically sp3 is associated with the atom I'm pointing to. Okay, so oxygen, nitrogen, and then this one's sp3 for tetrahedral. But what's planar? Oh, close. sp2. The way I like to look at it, you can count how many orbitals we have. So sp2, that's 3, right? So I have 3 groups around this carbon, so that's sp2. sp3, I have 4 groups, 4 orbitals, right? S and 3p's, 4 orbitals. But they're hybrid orbitals, don't forget that. So I have 4 of them. And I have 4 groups around nitrogen, 4 groups around phosphorus, 4 groups around oxygen, sp3. Okay? Now we could also have hybridization for sulfur. And that's the last one I'll go over. So there are 2 sulfur examples I want to go over. Both are notoriously smelling compounds. Don't know if you've ever been around sulfur compounds, but it's like being around garlic all the time. We had a research product where we were trying to make garlic compounds because of their therapeutic and pharmacological effects. I avoided the lab like every day. I went to the other lab. 96.5 degrees. So see sulfur as the, for sulfur in particular, and some phosphorus ones. I didn't show a phosphorus one that does this, but you see here the bond angle, it's kind of, it starts deviating from 109.5. So this hybridization model is just a model. It's not for everything. It doesn't support every compound. Okay, so you kind of use it as a way to validate what you get when you measure these things, but they're not supposed to be a solution for every problem that you encounter. Okay, so then this one, the smelliest of them all, dimethyl sulfide, CH3. Like this bond angle is even, it's closer to the tetrahedral angle, but still deviates. So you can, we will just say these are sp3 hybridized, but you see the bond angles, they're deviating from the ideal quite a bit. So these are exceptions. We could say these are so-called exceptions to the tetrahedral geometry. Okay, the bond angles, they're deviating a lot. All right, and that probably has to do with the size of sulfur if I were have to give you my best hypothesis there, but that's my guess. Okay, so what's the goal here? Our goal is to look at an atom in a bond, say a carbon-carbon bond, and predict what's the hybridization there, and be able to identify like what hybridized orbital is used to form a sigma bond between those atoms.
Can you
Okay.
just walk us through
Yeah.
how it's sp3?
Which one?
For the sulfur.
Sulfur, yeah. So we're still saying it's sp3 because it still has how many electron clouds around it?
4.
4. That's why, yeah.
Okay.
Any other questions? No? All right.
Wait, I have a question.
Yes.
So for the linear, what's the hybridization?
Oh, yeah, sorry. Thank you. What is it?
Is it SCP?
SP, yes. There you go. Yeah, no problem. All right. So now I'm going to go over hybridization. I'm going to give you like the breakdown of it. I'm not going to go into too much detail, but I'm going to show you like why we hybridize and why it becomes SP3, SP2, and whatnot. We might have forgot. Okay, so the little background here, because there are some questions on the homework that ask you. What's the hybridization of, say, this carbon-carbon bond, right? What's the hybridized orbitals we use? All right, so, all right, don't draw that line, okay. So let's do now hybridization. Hybrid orbitals. Okay, so the first thing you should do, look at electron geometry. Okay, so if it's 4, tetrahedral. What's 3? Trigonal, not pyramid. Planar, yeah. So we're looking just at electron geometry. And then two groups is going to be linear, okay? So either tetrahedral, planar, or linear. As long as you can identify those and connect it with them, the number of groups around the atom, you'll be able to pair this up easily, okay? So tetrahedral. So we have a few of them. So we're going to start first with tetrahedral. All right, so tetrahedral, let's underline that. So in your notes, this is something you can clarify. So tetrahedral will use sp3 hybrid orbitals. Okay? All right, so let's just draw a picture of the most common molecule that adopts tetrahedral shape, and that's methane. All right, so methane, 1.10 angstroms. Okay. All right. So angstrom is just a term for length, and specifically for chemists and like crystallographers. So 1 angstrom is like 1 times 10 to the negative 8 meters. So it's kind of in between nanometers and not picometers, micrometers. But that's what we use. Okay. And then each bond angle here, they're all the same bonds. So it's 109.5 degrees exactly. And that's the model compound we use for a tetrahedral shape. Okay. All right. So the one thing we had to point out is in this model, in this structure, right, all the CH bonds are what? They are all, yeah, they're all single, so they must all be identical in length, right? Are identical. Okay, so this is why we went over electron configurations, because it leads to this, okay? So carbon's electron configuration is 1s2, 2s2, 2p2, okay? But what part of this configuration is used in bonds, in bonding? Is it the 1s? Or is it the 2? Yep, the 2s and 2p. Both of them can form bonds to make an octet, right? So let's just highlight this region here. All right. These electrons are used to bond. But one thing we had to point out here is that the electrons are in different orbitals. All right? So that's a problem. If they're in different orbitals, that means they won't have the same length. Because which orbital is closer to the nucleus? Let's just kind of go back to Gen Chem a little bit. Is the S closer or is the P closer? PS, right? That's what we learned. Things are more spherical will tend to be, they'll tend to navigate, or the electrons will tend to be located closer to the nucleus, right? So a shorter bond distance, or shorter distance from the nucleus, right? All right. So what happens here is if we draw the electron orbital diagram, we would have it look like this. All right. So the problem with this model is that you have electrons everywhere, and in order to kind of, what's the best word, reconcile what we see and what theory says, we do something called hybridization, okay? So we're going to promote an electron here. What that means is I take one of these and put it right there. And it becomes, we have now the 2s. Wait, let me just write it so it's kind of level here. Because you might get confused if I don't do that. All right, so I promote that, right? That way I can form potentially 4 bonds, right? In order to form 4 bonds, I need at least 4 unpaired electrons to bond with other atoms to form a bond, right? So here we have pure s orbitals. Here are pure p orbitals, okay? So that's before hybridization. So we can think of hybridization as what? Not necessarily, I guess the best way to put it, hybridization is like kind of combining or mixing these 2 orbitals, and whatever we put in, so I give you 4 coins, right? You're going to give me out 4 coins of equal value of what I put in, or else we don't have a trade, not an equal bartering system, right? So what happens here is now you're going to hybridize. Maybe where should I put it? So you're going to hybridize here. Okay. Or I like to say, in quotation marks, mix. All right? Combine these orbitals, because remember, orbitals are mathematical expressions. You can express that using mathematics in a different way, and you combine them all, and you're going to get out 4 different functions, or say orbitals, of equal value, or like of equal energy. Okay? So we're going to get 4. What kind of orbitals? So if we combine all of them, right? So let's put a circle here. We're going to combine all of them. So we're going to get a hybrid of 1s and how many p orbitals? How many did we combine? All 3? 1 of the 3? 2 of the 3? All 3. So this will become sp3. And since we added 4 original atomic orbitals, we must conserve that fact, and we get 4 sp3 orbitals instead. So each s orbital is only 25% s. So if I have 4 s orbitals, I will still have total 1 s, pure s, right? Because each sp3 is only 25% s. Now, how much is each p worth? 75. And what's 75 times, well, what's 0.75 times 3? 4, I mean? Isn't that 3, right? Yeah, so 75 times 2 is 150, right? So 0.15, or, 1.5. And then times that by another 2, I get 3. So the sum of these orbitals here will equal the number of orbitals I started with. So it's all conserved, okay? And then we put an electron in here. Now look at here. All the electrons now are in the same orbital. So if they bond to hydrogen, they're all going to have identical bond lengths. So that's the rationale behind hybridization. Okay? All right. So here we have 4 hybrid orbitals. Now does it, do you guys know what an sp3 orbital looks like? It's a hybrid, so all hybrid orbitals look something like this. So you're going to have a, oh God, don't do equal sign. So you're going to have something that looks like a sphere, like a p orbital, but since it's merged with an s, it's going to be mixed. So it looks like an deformed or kind of like disoriented p orbital. So that's a sp orbital. So it looks like a p orbital, but not quite, right? And that's because one, it looks a little bit wider because it has S character, spherical shape. That's what it looks like. Don't worry, you don't have to draw it. I'm just giving you, it's just some information so you know what I'm talking about, okay? All right. So now how will this apply? What is this useful for? So now let's draw a molecule where I'm going to talk about these orbitals. All right, so here's the ethane molecule. C. All right, and after this one, we'll take a little break. It's kind of getting a little bit muggy in here. All right. So I'll tell you these bond angles, bond lengths. In grad school, you have an exam, an oral exam. I had to memorize these values, but you don't, so don't worry, okay? I'm just telling you, it's tough over there. All right, so 1.54. Are you serious? Sorry. 1.54 angstroms. Okay, that's the bond length. So I'm pointing to the bond here. Okay, that's the bond length. And this angle is about 109.6. So pretty close to tetrahedral, right? Okay, so now the point here is to be able to assign hybridization and sigma and pi bonds in the molecule, okay? So how many CH bonds do I have? C-H. Bless you. 6. Now are those sigma bond? Is that a sigma bond or a pi bond? Sigma, right? There's no p orbitals left, so we can't have a pi bond. So we have 6 CH sigma bond. Okay? And what orbitals are involved there in that bond? We could say now each carbon is sp3 hybridized. And we have hydrogen, but hydrogen doesn't hybridize, right? It only has one electron. So we just label it the s orbital. So hydrogen and all the halogens, when they're not central atoms, well, hydrogen can't be a central atom, right? Halogens, when they're just off to the side, they're not the central atom and only have one bond, like we have shown, those are unhybridized. Okay? All right. And then we have one C-C sigma bond. And the orbitals in that bond are CsP3. And what about the other carbon atom? What's the hybridization there? It's not a trick question. It's the same, yeah. So if I give you a structure, I might be like, I might ask you, all right, here's 3 different carbon compounds. They all have different carbon-carbon bonds because one's a single bond, one's a double bond, one's a triple bond. I'll ask you, okay, what hybrid orbitals are involved in this CC bond? And you have to write something like that. Okay? Okay. So I'll tell you right now here, each tetrahedral atom is sp3 hybridized. Okay? All right. Are there any questions on that example? If not, we'll take a break here, 10 minutes, and then we'll continue off. So we'll pick up at 2:10. All right? We'll talk. Get a break. It's kind of hot in here. Yeah. Might be we're kind of backed up, so I'm not sure if this problem will be resolved by this week.
Well, it depends also on like the elements, so like, because it has like 4 bonds, and it's all 3 still. Like again, when you, like if you had like H2O, you know that it's like 2 hydrogens, 1 oxygen, so the oxygen is the central atom, this hydrogen separate, and then 2 H's branching out, and that means there's 2 electrons on top of make it bend. I don't know if you remember from the lecture in C1A, so like, yeah. So you have linear, trigonolinear,
Yeah.
so for example, it's like, this is based on electrical geometry, that's what he's specified, so we're not looking, so this is considering lone pairs. So like, for this, it would be trilinear. This is, 1 lone pair is considered one of the branches going up, so like H2O, sorry, H2O. Here would be 1, 2, 3, 4. That's the tetrahedral. Okay. So you have to count how many bonds and how many bonds there are.
It is really
So it's 4.
Yeah.
Yeah. Okay. You have to count all you're writing your notes. You're like, if I'm not. I swear, like writing it on a piece of paper, it's different. It's different than this. Like I swear, like the information, like I absorb it better or something. And I was
You might like coaching better than the. There's not that much math.
I mean, doing good. I like this, like grabbing, skills quickly, but maybe I'm gonna try to like
Yeah, but it'll pick up.
every weekend just read or watch the lecture and then write it out. So it's like, so you're just a double. Because it's easier to write during the lecture than like writing out. Like, so you have to bring it and then I hate if I shoot different words. But then already having it and like rewatching it going back and writing it and try to make it up.
I'm gonna get my whiteboard. Because I mean, what did you say for the blue top one chart, SH4,
This is not a pilot. I'm really gonna go today to see this back.
Maria, wanna shoot our class on Monday? We have a lab. No. It's okay, we finished early. Raven taught us this way super quick. It was just like Excel, it was easy. We finished, but he didn't let us do the last activity. He said you have to wait until Wednesday because he wants to.
He's not here anymore. We're all.
He said he's not gonna push through.
No, they even let him in.
Even on the waivers?
Yeah. He was,
Oh, yeah.
he was too far, I think. But it let him register.
I told you every now it's only
So
I'm stretching, pushing just wait until at least this week. And if not, Palas, you don't have to come anymore. I don't know how to do it.
When is the quiz?
Yeah, like review.
Do I have to take the quiz or someone
I don't think he'll let
It
you.
really does feel like.
Okay. So take the answers from you.
Yeah. We missed you. Are you okay? Were you sick?
I thought you dropped.
Did she tell us?
Yeah, I told you that.
I
You
know.
said,
I'm getting notifications.
Jessica
When
told us.
Jessica
I was like, maybe you
She
should.
was like, Maria said she can't come, and I was like, where did she send that?
Yeah.
I don't know next door. We have like that's because of every.
Yeah.
That's the one where all the last year before we had a spot for you. Yeah, it's good. He's great. So like, you did a 10 out of 10. You did.
I got to get the cabin and
So that's not a No. I asked my other friends, they didn't get a chance. I asked I asked him why he hated anyone in his because you all should have captions.
I talked about my.
That he never said to write a caption, and he said yes. And there's captions on the rest of the not gonna lie, like I was too lazy. Like I submitted it even after you sent it. I didn't want to go back. I was like, I don't need it. The only problem is like at 9 out of 10 drops at like 9. You know. So why does it drop 153?
Still buggy in here.
Well, I don't have the original too.
All right. On here. All right. All right, everyone. Welcome back. Temporarily, I guess. All right. So we left off with tetrahedral. So now let's settle down, come back. All right, planar geometry. That's for trigonal planar molecules. So let's just go over there. Planar. Okay. So trigonal planar is for what hybridization? SP2 or SP? Yes, SP2. So here we could say SP2 hybrid orbitals. Okay. So SP2, one of the most common kind of geometries we see, especially in alkenes. And those are things that are everywhere. Okay. So the simplest alkene here in organic we have is ethene. Okay. So the double bond here, we can see if we compare it to the single bond, it gets now shorter, which makes sense because a double bond has double the shared electrons. So that means you're going to have kind of double the force between the two atoms, okay? So this bond angle here increases to about 120 or 120.7 degrees. Okay. And the hydrogens thus will decrease a bit because they're being pushed out by the pi bond. Okay. So the carbon double bond has one sigma bond and how many pi bonds? One. Thank you. Okay. So like in tetrahedral, we're going to do the same hybridization thing, but we are not going to combine all the p orbitals. So we only combine these two. So we're going to only hybridize those in the box, okay? 3 orbitals are combined. Okay, when we go to hybridize, all right, so we're going to get 3 sp2 orbitals. like that, okay? So what happens to the other p orbital? Yeah, I'll just stay here, right? And here we must make this distinction, not hybridized. Okay, it's not going to be hybridized in this case. All right, so how does this hybridized orbital look like in this molecule? Let's redraw. I drew this last week, but let's just redraw it again for clarity. All right, we have our carbon here. This bond right here is our single bond, okay? And I'm just going to draw these as dash and wedges just because we're just going to look at this compound on its side, so it's no longer flat. It's kind of coming out to us, okay? So the p orbital will look like this, okay? And if we kind of shade it like that, that will tell us that's how it's being connected through the pi bond, okay? So this right here is our pi bond. Where's the sigma bond at? If I were to point to a line, where is the sigma bond at? Yeah, this one right here, right? So pointing out there, that's our sigma bond. Very good. All right, so based on this structure, let's now write down all types of bonds we have. All right, how many CH sigma bonds do we have? 4. Very good. All right. So, of the sigma bonds here, we could say the carbon has sp2 hybrid orbitals, and the hydrogen still has just the s orbital. So that's the bond, that's how it bonds. Hybrid orbital and the s spherical orbital. Okay. So we have one CC sigma bond again. Okay. And this is going to be CsP2, CsP2, like before. So that's why that's the hybrid bond. Okay. And then what other bond do we have? Pi. So one CC pi bond. And what orbitals from the carbon atom does that bond come from? Yes, the p orbitals. The empty p orbital. Sorry, not the empty p orbital, but the unhybridized p orbital, like that. Okay. All right, that's sp2, okay? So any double bond you see in a compound, that counts as a pi bond. And the carbon atoms or the atoms in the molecule that have a double bond, as long as there's only one double bond, okay, connected to it, it's going to be sp2 hybridized. All right. Are any questions on trigonal sp2? So you only need to know sp, sp2, sp3. There's no need to worry about the d orbitals because you guys already seen that in Chem. No, we don't see that here. Okay, so we've talked about planar geometry. Now let's talk about linear. So let's do one more. We're almost done talking about the hybrid orbitals, okay? All right, so let's talk about linear geometry now. All right, so the simplest sp hybrid orbital is carbon dioxide, but in organic, we like to talk about acetylene. So like an acetylene torch uses this compound here to get that high flame. All right, so this bond angle right here, 180 degrees. Okay, 180. Why is it 180? Yeah, it's because it's a line, right? That's the 180 degree, right? Okay, so notice here the bond angle gets even smaller, 1.20 angstroms. All right, so bond angle increasing, and that's because you have less things around the carbons. And then the bond length is decreasing, getting shorter, because you have more electrons pulling the atoms closer together, right? All right, so in the triple bond, we have one sigma bond. And then what's the other two bonds? What kind of bonds are those? Yeah, 2 pi bonds, right, good. All right. So again, we start with the same hybridization scheme, 2s and then 2p. So it's still promoted through all these atoms here, but we only take now 2 orbitals instead of 3 like we previously did. So we're going to combine here. 2 orbitals are combined. Okay, so we're going to hybridize here again. Last time we'll hybridize. All right, and we get 2 sp orbitals. And then the p orbitals are still unhybridized here. So here are the rest of these 2 p orbitals. Unhybridized. All right, so those are unhybridized because they're going to be used, like we saw before, to form the pi bonds. So they can't be involved directly in bonding with other atoms. Okay, so there we go. We get now 2 hybrid orbitals. What we put in is what we get out, the same number. All right. So drawing this is a little bit tricky, like we saw last week, but I'll try my best to draw it as clearly as possible. All right. So 2 orbitals hybridized, the rest are unhybridized. So let's draw this now. Instead of drawing it lengthwise, let's draw it in diagonal fashion. All right, let's do the different color now. So what I like to do here is try to draw it like this. Okay, so these bonds are interacting here. And then, so that's 1 pi bond, right? Now, there's another set of p orbitals that must form the triple bond. So what I like to do is do something like, oops. And if you could just bear with me, the red are interacting with the red. So it's kind of hard to see in this graph, but they're perpendicular to each other. So they're actually in different planes interacting. So you have one p orbital kind of like orienting here, and then another that's perpendicular up and down. That's where the red comes in, and then the blue comes in the back. Okay, or in the front, and that's how you visualize it. Okay? So it might look like a lot going on, but that's how the triple bond exists between these 2 atoms. Even though there might not be enough space, it's in a different plane or a different dimension, so to speak. So that's why they're not overlapping directly. Okay, so let's go along here. How many bonds we have? So we have 2 CH sigma bonds. Okay. All right. What hybridization does the carbon have now? sp. Good. And then we have 1 CC sigma bond. So both carbons now CSP, CSP. All right. And how many pi bonds are there? 2. So we're going to have 2 CC pi bonds. Very good. All right. And doesn't matter, just say CP-CP. Okay? Indicating the subscript indicates that This bond is formed through the p orbitals on adjacent carbon atoms. All right, is that clear? Any questions? That's hybridization. Catherine.
Clarify, so we have two hybrid orbitals of sp, but then we have like 3 sps used in the bonds?
Where?
For the sigma bonds, like the CH, CC sigma bonds.
Oh, I see what you mean. So they're all so actually they're not actually 3 different sp orbitals. I'm just talking about two of the same carbon atoms. Yeah. So each carbon atom, right, will have 2 types of orbitals between it. So here's C and C, like that, right? So this is that's the CC bond, right? So these are both sp orbitals. So sp, sp. Okay? And then the other half of it, you're going to, this is the H, like that. Yeah, so this one here would be the CSP, H right there, 2 of those right there. And then the CC bond that I'm pointing to right there, this one right here, the center one right there, that refers to this bond in the center right here. Yeah.
So the numbers are technically for the whole molecule, there's technically 3 sp or sigma bonds in the whole molecule.
Yes.
Only 2 for each carbon.
Yes, right. So each carbon has 2 sp sigma bonds, and then one's to the hydrogen on one side, and one's to the adjacent carbon atom on the other half of the molecule, right? Yeah. Good. Any other questions? All right. So the goal here is if I point to a particular bond in the molecule, can you tell me like what orbitals are involved in the bonding? So like sp, sp2, sp3, that sort of thing. And it correlates too with the homework, some of the homework problems I've shown. All right. Any other question about hybridization? Any? No? All right. So we're building up these skills because we're as we work our way through this course, these skills are elementary. So I won't refer back to them as much, and during class. But if you have any questions about them, you can feel free to ask me during office hours or email me. Okay. All right. So now we talked about hybrid orbitals. Last thing I talk about is resonance in chapter 1. Okay. So let's flip to a new section here. Now we're going to talk about resonance, and maybe we've seen resonance before, but we're going to revisit it, okay? So let's label this subject resonance structures. So in major and minor contributors. So in Gen Chem, you probably learn about what resonance structures are, what a minor and minor contributor are, but you may have not delved into why this matters, particularly in reactions, okay? So in organic, we will refer to resonance structures all the time because they point to us what part of the molecule is particularly reactive, and how do you know that? And if you draw a resonance structure, that kind of tells you why that is. Okay, so in resonance structures is correlated with reactivity, and we'll talk about more about that later. But first, let's go back over the basics. So there are a few rules we should remember. 1, only move electrons in pi bonds or lone pair all right, so either in pi bonds or lone pairs. So those are the 2 sources of electrons you can freely move when drawing resonance structures. you should never move physical atoms. So don't move the atom, like in one structure, don't move the atom to like the other side or something. That's not a resin structure. That would be an isomer if you move the atoms around, okay? So 2, never move atoms, or we say electrons in single bonds or sigma bonds, or sigma bond electrons. Okay, so don't do that. Don't move those. Never move those. Okay, and we'll practice with some. Okay. All right, 3. So what's the difference between two Lewis structures, right? That qualify or count as resin structures. What's the difference? The only difference is the placement of pi and non-bonding. So non-bonding means like lone pairs. That's just another way to refer to them. Non-bonding electrons differ. All right. So the thing that does never differ between resin structures, okay? So the thing that does not differ is hybridization nor the skeleton of the molecule, right, of the atoms. So neither of these two things change, okay? They're constant. The hybridization is always the same, and then the placement or the skeleton of the atoms, like the mapping of all the atoms, they're the same too. Okay. All right, do these things sound familiar? Like when we draw resin structures, we only move the pi electrons or the lone pairs? Let's go over some examples. All right, so I have a few examples I like to go over. Okay, so here's some examples here. So the thing I want to really kind of send you with is that resonance are imaginary. Okay, they don't represent the molecule 100%. They're just forms of the molecule that give the overall picture. It's like you yourself are not a splitting image of just your mom or your dad. You're a mix of both, right? You can't just say your dad represents you. Your other side also represents you, right? Real structure is a hybrid, so a mix of both. All right, so let's use one example. Let's use this first example. So this is a reactive molecule that we'll talk about, probably not in this class, but if you have to take the second one, that class. Okay. So this is an intermediate called an enolate, because it's an alkene, but has a negative charge on oxygen. That's called an enolate. Okay, but don't worry too much about that name for now. All right, so there's another way we could draw this molecule. Okay, so you might think, okay, how can I rearrange the double bonds and the electron pairs on oxygen to generate another, say, resin structure? All right. So we're going to learn how these we call electron pushing arrows work. You start from an electron source and you point to an atom or point between two atoms where you're going to form a new bond. Okay? So I'm going to take this arrow and start from the electrons and point between the two atoms where I'm going to make a new bond, okay? And then, in order to avoid disobeying or violating the octet rule, we have to move these bonds over to carbon, okay? And then if we use a double-sided arrow like this indicates you're talking about two resin structures. So the other structure here, we're going to draw the result of those arrows that we just drew. So this double bond will break. This carbon here will now have a double bond to oxygen. And since I've used one of those lone pairs, I will now have two lone pairs here instead of three I had before. And then I have to draw a lone pair here because I broke the double bond. When you break a bond, you have to take both of those electrons and put them somewhere, okay? So that's where it ends up, and we get a negative charge here. And usually when we draw individual structures, they must be encased in brackets because, quote unquote, imaginary, okay? So these are imaginary Lewis structures. Okay. So the point is here, so what's the actual structure, right? Well, the actual structure is what we call hybrid. So if you were worried about the actual hybrid structure, we would draw something like this. So notice here in my two structures, the atoms are conserved, but what's also conserved? Think about, in addition to the lone pairs and all the atoms and bonds, what else is present? Charge must be conserved. Okay, if you don't have the same charge, something went wrong. So make sure you balance the charge too. Okay, so notice here that both structures they look kind of similar. You just put the one lone pair on a different atom, right? So that actually matters. One is more stable than the other, and we'll talk about stability a little bit. Probably not today, probably next time. But here's the hybrid. So let's draw a different color. The hybrid is this. So when you draw the hybrid, okay, you have to remember, the double bond, the placement of the double bond is not set in stone, or it's not set. It's not what we say localized. So the double bond and electrons in the double bond are delocalized, meaning they're not specific in one location. They are moving around, okay? They are not, they're not restricted between two atoms, okay? So how we draw this is we indicate that this double bond is migrating by using dotted lines. Boom, 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 like that. And here's to the oxygen atom. Here's to the H. Now, if those are dotted lines, then the charges must also be non-permanent. So the charges are partial charges now. So here, we're going to have a partially negative charge. Okay. And we're going to also have another partial negative charge, but let me just double check something really quick. Okay, yeah, I thought I wrote it. And then the carbon will also have a partially negative charge, and that's because in one structure, where's the negative charge at? Carbon, and in the other structure is at the oxygen, right? So that's why it's partially negative at both those atoms. Okay? All right. So this is the actual, so this is called the hybrid. Hybrid will always have these delta partial charges and these dotted lines, okay? So this is the actual structure. So it's a mixture of both of these structures combined, okay? So we can't just pick and choose one, all right? They're both part of the overall structure of well, we won't call it a stable compound. It's a intermediate, okay? But this structure, okay? All right, are any questions? How I drew these arrows? So usually when you read resin structures, you read left to right. So the arrows are always originating on the left, and then the resulting structure is always on the right. All right, does this seem familiar? Yes, in the back.
For the actual structure, you don't have to include the Lewis dots?
Oh, you probably could. I would just, I would keep them in there. That's a good point. Let's just keep them in there. Yeah. Those dots will always be there. Yeah. Good point. Thank you. Just to be consistent. Okay. Yes, that's true. You should always put those in there, especially since these are Lewis structures. Let's keep all the lone pairs. Yes. Okay.
In that case, the dotted line, does that count for the extra lone pair that?
Right, because it's moving. Yes. Right. You got it. All right. So the last bit of time, let's start going over equivalent resin structures and non-equivalent. So equivalent is pretty straightforward. Non-equivalent, we'll have to break it down. How do you determine if something's a major contributor or minor? Okay. So let's start first with just equivalent and non-equivalent resin structures. All right. So this was our example here, right? So now let's talk about the prime example of resonance is benzene. All right, that didn't work as I planned. Okay. All right. Sorry, you guys, that's a hexagon. Okay, so benzene, you have alternating double bonds. So if I move it in a clockwise fashion, the double bonds will now appear where? It looks like it's moving in a clock, right? So they're just going to alternate one position to the right or in a circle. So now I have two resin structures. And you might say, oh, I could just flip that over and I'll get the structure on the left, right? If I take the right structure and I just like invert it like 180 degrees, won't I just get the structure on the left? Yes. So that's why these are called equivalent resonance forms. Okay? Now, if they weren't equivalent, there'll be like a big difference between them. Like say, oh, one of the bonds is bonded to oxygen, double bond to oxygen instead, and a double bond to carbon. That might be a difference. Like the one we saw in the above example. Those are not equivalent. Okay? Let me show you another example of not equivalent. So, and then we'll probably end it there. All right. Remember, we saw positive charges before, right? For carbon, that exists. It's kind of hard to prove that they exist because you have to kind of trap them, kind of like they're not very stable species. So it's really hard to prove the existence of these without the use of spectroscopy. Okay? So now this is a resonance form too. Okay? So imagine here we put, let's see, let me just draw this structure and I'll ask you guys how I got to this structure. And you could just, just shout out where the arrow you think where the arrow should be. So in organic, we frequently circle our formal charges. You don't have to do that if you don't want. It'll just help me for grading and clarity. So I would appreciate that, but you don't have to do that, okay? So I have two resin structures here. How do you think I got the right structure? Where did the arrow originate from?
So one of the lone pairs
One of the lone pairs, right? And which way do I point it?
or the carbon.
Toward the carbon. So we're going to take this arrow and put it right there. Okay, and that's how I got that structure. This is an example of non-equivalent resonance forms. Okay, the reason they're not equivalent, right? Do those structures look the same? Not really, right? They have different kinds of bonds between between carbon and oxygen. One's a single bond, and the positive charge is on carbon, and one's a double bond, and the positive charge is on oxygen. So they're not the same. Okay, so well, which one's more stable? Let's go over the first guideline. Okay, so how can we tell if which one of these forms is more stable, more preferable? Okay, so now let's talk about guidelines. Okay, to relative stability. So relative meaning you're comparing it on a comparison scale. Guidelines to relative stability of non-equivalent resonance forms. Sorry, that's a lot to write. All right, so rule number 1. All right, so rule 1. The first rule has to do with octet rule. So all atoms should obey the octet rule. Okay, so all resin structures should obey octet rule. All right. All right, so the first, let's just rewrite the first example we did. Remember how we wrote it like this? All right. So we wrote it one way, right? It went one direction. The negative charge moved to the carbon atom. All right. However, could we have moved it? Could we have done this? Boom, 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 boom. All right. Well, so would this have worked? No, what? Yeah, carbon has too many bonds, right? So one of these carbons has too many valence electrons. So right here, too many electrons. So that doesn't work, right?
Isn't that true on the middle one too?
What do you mean?
For the left-hand carbon with the lone pairs?
Ah, this one?
Yeah.
Yeah, but does that disobey the octet rule though? So we have, let's just go over that. So we have 2 electrons here, right?
Yep.
2 per bond?
Yep.
So that's still 8. But what about this carbon? How many are around that carbon?
10.
Yeah, 10 electrons. So you might think, oh, let's just move that double. Let's just make that a double bond. But you have to obey the octet rule. So this would be bad. So let's X this out. No good, okay? So that's not a good rule. Do we remember that? Like we always want our row 2 elements to have at least an octet, especially carbon, nitrogen, and oxygen, and fluorine. Hopefully that we remember that, okay? There will be a lot of rules though. Okay. So, all right. All right, I'll just write rule 2 here, and then we'll pick up on Thursday, all right? So rule 2. All right. Structures with maximum octet are the most important contributor. By that I mean form, okay? What does it mean when I say max octet? What do you think that means? Does that just mean one atom with an octet? No. So this means almost all the atoms have octets at least. So if all the atoms have an octet and you don't have any atom with just less than an octet, that would be considered more favorable. So most atoms will have octets. So here, if we look at this one on the right, that one had more than an octet, so no good. And the other two on the left, all those atoms, the carbon and oxygens, they have at least an octet. So that's the most favorable guideline to drawing resin structure. And we'll go over the rest next time, okay? And do more examples. All right, that'll be it.